Hello, everybody. Welcome to calculus. All right, so today what we're going to do is we're going to start calculus out by talking about limits. Okay. Uh, to let you know, the concept of a limit is actually central to calculus. To understand calculus, it's essential to know what it means for a function to have a limit and then how to find the limit of that function. And this is kind of what we're going to talk about today. We're going to cover a lot of things, but these are the main objectives of this whole entire lesson. Now, for those of you who are doing this remotely, you're going to see this broken down. That way you can just go and click on a specific link if you need to replay just a specific part of it. Okay. So what we're going to talk about is we're going to talk about the use the definition of a limit to estimate limits. We're going to determine whether or not limits actually exist. And then we're going to look at a bunch of properties. I believe with limits, there are 9 properties total. And then we're going to look at direct substitution so we can evaluate these. Okay. So the definition of a limit. So the notion of a limit is fundamental concept of calculus. To begin this whole entire thing, we have to ask the question, well, what does it mean for a function to have a limit? What does that mean? How do we look at this or whatever else? And it starts off by this. If f of x, which is the same thing as y, becomes arbitrarily close to a unique number L, as x approaches c from either side, then the limit f of x as x approaches c is L. And this is how it's going to be written. Now, you're probably thinking, I have no idea what you just said. So let me talk about this. So if we're looking at this piece here, we have the limit of f of x. Well, everybody knows f of x is your function, okay? So remember, f of x, that's going to equal your function. All right? As x approaches c, so we have some x value, or we have some value on the x-axis that we're going to look at here, for instance, and we are going to approach this value somewhere on the x-axis. So this c value here is actually going to be the actual x-axis, or not x-axis, x value that we are going to focus on. And then when we get to that point, your answer is going to be L. Well, L is simply your y value at that c value. Okay, so to make it a little bit easier, the value of f of x can be made as close as we please to L, your limit, that for x sufficiently close to c but not actually equal to c. And so that's the whole topic of limits. So if you think about this, and if you look at the picture that I put in here, we have a speed limit sign here, and the speed limit sign says 15 miles an hour, and you see me running. Yes, this is my Bitmoji, and yes, I have a crown. Yes, I'm cute. Okay, so I'm running. My speed limit is 15 miles an hour. So what this is saying, if I was actually able to run 15 miles an hour, I would be doing something like this. And then when I get up here to 15 miles an hour, I'm going to level off. That is not level. Let's try that one again. So again, I'm running, and then I'm going to level off. There we go. That's a little bit more level. This leveling off piece is my limit. I can't go past the speed limit of 15 miles an hour. So I can approach 15 miles an hour. In some cases, I can actually reach 15 miles an hour. But I can't be 15.01, or 15.2 or 15.9 or 16 or 17 because that goes over my limit. But I can come up to that limit, reach 15 miles an hour, and be done. But that's assuming that I'm going to start off at 0 and I'm going to go forward and go up to 15 miles an hour. The other way I could do it is I'm driving 65 miles an hour and I get to a school zone and it slows me down to 15 miles an hour. So that limit can come from either side. But how you look at it is when you're looking at the definition of a limit, I've got this fixed point, the school zone. This fixed point says, okay, at the school zone, I can go anywhere up to 15 miles an hour, but I can't go over 15 miles an hour. So I'm either coming off the highway and slowing down, or I'm coming out of a convenience store and speeding up. But the point being is I can't go over that 15 miles an hour. Okay. So again, when we are talking about that whole little limit of f of x, so let me just write this down. So your limit of f of x as x approaches c is equal to L. Okay. This here, the stop sign in this case, is my L because that's what I'm trying to get to. Once I hit the actual stop sign, that is my limit. Me approaching the stop sign from either direction, that's going to be the X value. So however far I got to go, when I get to here is my X value. And when I actually arrive, that's my L value that I have to look at. Okay. So there are three specific ways that limits can actually exist. Let's look at the first one. So if I give you a graph and I'm asking you, okay, I need you to look at a limit at this specific point. You're going to pull this point up and you're going to say, okay, here's my graph. Here is the point that I want to focus on. So what I'm going to do is I'm going to go over to that point and I'm going to go up and I'm going to look at it on this graph. Now, one of the things that you have to notice is that if I'm looking at this limit, so if I'm looking at this graph right here and I'm approaching this A value, the first thing I got to ask myself is this a continuous graph on both sides approaching this point? As long as it's continuous, I can find this limit. But the moment that this graph, this whole thing here, the moment that breaks up at that specific point that I'm focusing on, it's no longer continuous and I can never get to it. Okay? So that is one of the key things. You always have to make sure that what you're looking at, that your graph is actually continuous. So here's one example. I have this graph, it's continuous, and I have a closed dot, so that means this point actually lies on the graph. So as long as I can approach it from this side and from this side, and I'm approaching the actual dot here, which is good, so everything falls into place, then I have a limit. I can actually come up with this Y value that's sitting right there and say, hey, yeah, I'm actually approaching this value, so I'm good to go. All right. This is your best case scenario. This is what you want. 99% of your graphs or problems or whatever you're doing, you want this because this is the easiest thing to do. The second way is you have the same graph, but now at this value that we're looking at, in this case A is not defined. It doesn't mean it doesn't exist. It's just not defined here. It might be somewhere else, or maybe it really doesn't exist. We don't know. But what we do know is somebody took the manhole cover off of the manhole, and now we have a hole in our graph. So we more likely have, remember vertical asymptotes where you had either the wall that you came up to or the manhole cover? Well, here we have a manhole cover. So what happens is on this graph, I'm still continuous except to when I get to this point. Now, when I get to this point, I have a hole, so I have to stop. So when I look at it from this point of view over here, I get to that same hole, and again, I have to stop because, again, I can't go anywhere. But the neat thing is the question you should ask yourself is, am I still approaching the same number from both sides? In this case, the answer is yes, I am, because if you look here, I'm coming in from this direction and approaching that number. I'm coming in from this direction and approaching that number. So therefore, this limit exists because I'm coming in and I'm approaching the same value, which is whatever that is, whatever it would have been. Okay. The third way is where it is defined. So your X value is defined. I actually have a Y value to go with that X value, but it's just not on that graph. again, this is okay because, again, the purpose of a limit is what am I approaching? I have to be approaching something. So if I'm looking at the graph, I'm still approaching something from both sides. So I'm good. Everything is good. I have a limit here. Now, here's the thing though. The limit here, what I would be normally looking for, is this answer here is not the same thing as what my actual Y value is in this case. Because somebody has picked up my manhole cover and instead of sticking it in their back pocket and taking it home, they took the manhole cover and put it across the street somewhere. So it's still there, it's still in the vicinity, but it's just not on this graph where I need it to go. So when I'm looking at this whole graph and I'm talking about a limit, my Y value at A here doesn't necessarily have to be defined, or it can be defined. It could just be somewhere else, but that doesn't mean that that's going to be my limit. Okay. So on my graph, I'm still approaching the same value on both sides. However, my actual value at that A value is not the limit, but I do have a limit that exists. Does that make sense? I'm hoping that makes sense. And if it's not, I'll show you later on because I got some examples that will actually hopefully clarify this a little bit more. Okay. So when we're looking at this, we have these three ways here that's going to help us look at, do we have a limit? And so if you have one of these three scenarios right here, as long as you have one of these three scenarios, you're going to have a limit that exists and you're going to be able to give me an answer. Okay. But you have to remember, you have to be approaching the same value from both sides. That's the key. If you don't approach the same value from both sides, you don't have a limit. So let's look at finding limits from a table. So to find a limit from the table, what we're going to do is we're going to evaluate your f of x at the chosen values around your, in this case, I'm going to use c. I don't know why I switched, I just did. But around, in this case, a c value. So I'm going to say, here's your function. What's the limit as x approaches 7? And so we're going to look at 7, but not look at 7 directly. We're going to look at all the values around it to see if those values actually come in approach that the same number on both sides. Okay. So we're going to take, like, instead of 7, we're going to take like 6.9, 6.99, 6.999, so on and so forth, however many numbers that you need on the left-hand side. And on the right-hand side, we're going to take 7.01, 7.001, 7.0001, and so on and so forth, and make sure that we're actually approaching the same number as we actually look at the number 7. So we have 5 steps. So when we're looking at a table, we're going to look at or use a table to find limits. We're going to follow these 5 steps. So I'm going to give you a limit, and I'm going to say, here's a limit. What I want you to do is I want you either to look at the table or put this into a graph, or not a graph, I'm sorry, a table, and I actually want you to tell me what this limit is. So the first thing you need to do is look at the limit and determine what your f of x is. The second thing you're going to need to do is create a table with the c value. So as x approaches c as your middle value. So whatever your c value is, that's going to be the dead center of the table. And then you're going to find numbers. You are going to be the person who drives this. So it's not going to be filled in for you. You're going to have to be able to figure out what numbers do I need to use. So you're going to go in and say, okay, I want to use these numbers that are around this c value, that are approaching the c value. So you're going to pick that, but you never want to actually be c. You actually want to just get as close as you possibly can. And then what you're going to do, once you do that, you're going to take a look at it, and then you're going to evaluate each one of those values and get an answer. And then you're going to determine, well, what number am I approaching? Am I approaching the same number from the left side into the right side? And then if you are, then you just take that c value and plug it into the equation and then get an answer. Or you can look at the graph, or you can look at the table and just draw your deduction from that. So let's look at an example here so it actually can bring some of this to life. So use a table to estimate numerically the limit the limit as x approaches 2 of 3x minus 2. So this is what the problem's going to look like. And what I'm going to want you to do is I want you to use a table, and I want you to estimate. So what I'm saying is I know you could just probably plug this in and get an answer and it'll be done, but that's not what I want you to do. I actually physically want you to use a table so you can see what's actually happening. So the first thing you're going to do is you're going to find out what your f of x is. So we're going to let f of x be this piece right here. Okay. So once you do that and you figure out, all right, that's the f of x, then I'm going to take this value right here and I'm going to create a table, and that value right there, that's going to be my dead center value. And then I'm going to pick numbers. I can pick 3 numbers on both sides, left and right, so you'll have 7 numbers total or 9 numbers total, however many numbers you want to have. But you're going to have all these numbers that are getting closer and closer and closer to the number 2 in this case. Okay, so let's take a look at that. So my table should look something like this. So here is my C value or A value or X, whatever you want to call it. Here's my value right here. So this is the number in question. Okay. What I'm going to do is I'm going to pick some numbers that are less than. That's going to be this side over here. And then I'm going to pick some numbers that are greater than. But if you notice, these numbers are not that far away from the C value that we've been given. So the next thing I want to do is I want to start filling out this chart. So I've got my X values that I'm going to look at here, and I'm going to fill out my charts. I'm going to fill out that one, that one, and that one, that one, that one, and that one. And this is where you have a calculator. So just plug this into the calculator and fill out your chart. And you should get something that looks like this. And then so now if you notice this, you will notice as I approach the number 2, my numbers are getting closer and closer and closer to what number here? Okay. And that's what you want. You want something like this because as long as this happens, that means that you have a number that you have an answer at that specific point. That means that your limit exists. Doesn't mean necessarily that the y value will exist with it, but there is a limit that will exist with it. And so if we're looking at this, then we'll notice a 3.997 and 4.003. So this is around the number 4 here. So we're determining from the table that that's going to be the number 4, which is correct. And then now you can check. So sometimes you're going to be able to, sometimes you may not be able to. And that's really going to depend on what they give you as an actual problem. So since they gave us an actual function, 3x minus 2, then I can just say, okay, well, I'm going to take this 2 and I'm going to plug it into my function, and I'm going to evaluate that and find out that the answer is still going to be 4. The other way is you can check by graphing. So there's 2 different ways you can check if you're given the actual function. You can look at the graph here and notice that I'm approaching the same value from both sides. Or you can come over here and say, okay, well, I'm just going to plug it straight in. So I got 3x minus 2. Well, I know that the x value that I'm looking at is a 2. Let's try that again. So since I'm actually going to evaluate that, I get 4 as my answer. So you have a couple of different options on this one. Okay. These are hopefully not as scary as it looks. That's, we don't want it to be difficult or anything. And I'm trying not to make it difficult or anything. But really, when you're looking at limits, this is the approach that you want to take when you're talking about tables. The other way that we can do it, it's going to be through graphing. But before we do that, I want you to take a few moments and I want you to pause this video and I want you to see if you can figure out what this limit is, okay? So I'm going to give you a few moments to do this and then hit play when you're ready. Okay, so let's see how you did. So if you've done everything correctly, you know that you're going to take this 3 that's sitting right here. Let's pick a different color. this 3 and you're just going to plug it into here and get an answer. So if we've done that and looking at that, we can wind up with the answer being 36. And so when you're looking at the actual table, your table should look something like this. So if you notice, when I was here, I said we could just plug it in. Well, sometimes you can. But when we're looking at a table, you want to kind of make sure, so you want to kind of get used to that. So you're going to just take your values from around that number there. And so if you notice, I'm approaching that number 3 because that's what it told me. So I got my numbers here that are approaching 3 from the left and approaching 3 from the right. And if you notice, I'm really, really close to the number 36. And so when I plugged it in, that's what I wound up getting. Okay. Again, if you have questions, make sure you're sending me a remind. Make sure you're sending me a text, not a text message, because that is a remind. Something like in the email or something or whatever else. But please make sure you ask questions if it doesn't make any sense to you, okay? So now, let's look at graphing. Finding limits from graphs. So we kind of already talked about this when I showed you that graph earlier. If I give you a graph, you're literally just going to read the graph. The key thing that you need to make sure is make sure that it's continuous with no asymptotes in it. Now, mind you, it can not be continuous as long as it has a hole in it and you're approaching the same value from both sides. That's okay. So when we're looking at a graph, we want to make sure that we're approaching the same number from both sides. That is the key. And again, you must approach the same value of f of a, whatever it is, the y value on both sides in order for the limit to exist. Okay? So let's look at this one. So if I'm trying to figure out what the limit is as x approaches -2. So I'm going to look here. So this is my value that's in question is right here. So I'm going to look at values from this side. And I'm going to look at values from this side. And I'm going to notice I'm approaching the same number. Now notice that at -2, I'm defined here. Okay? Don't care about being defined because that's not what the question is asking. The question is asking what's the limit. So the limit's only going to be on the graph. So if you look at this, as I'm approaching this -2 here, what number am I approaching? So if you look at it, you are actually approaching the number 5. Okay. So from this side and from this side, I am coming up to the number 5 that's right here. Now, I can ask the reverse of you as well. I can ask you, my limit is 7. What is my A value? What number am I, or what, if my limit is 7, what X value am I coming up to? So if I'm looking here at 7, I just come over here on my Y-axis and I come over and notice if I'm looking at this, I got to look at, well, am I continuous on this side? Yeah. Am I continuous on this side? Yeah. Am I approaching the same number? The answer is yeah. So then I just read straight down and you will notice as X approaches 4, I'm getting closer to the number 7. Okay. So you can be asked either way. So as an X value, I give you the X value, you tell me what that Y value is going to be, or I tell you the Y value and you tell me what X value that I'm actually using. All right. So we talked about what a limit is and what it looks like. We talked about what it looks like in a table. We talked about what it looks like in a graph. So now let's talk about properties. There are 9 properties here that we are going to be using and talking about, and you need to make sure you commit these to memory, okay? So let's start. We got 9 of them we're going to go through. And I got examples for each. We're going to start with the first one. Limit of a constant. Basically, what this is saying is if I give you a limit and I say the limit as x approaches a of c. So I'm basically saying y is equal to c. So I've got this horizontal line sitting here. I want to know what's that limit. Well, if I've got a horizontal line that's sitting here, and that looks like a G, not a Y, sorry. If I've got this horizontal line that's sitting here, and I'm doing something like this, regardless of which way I'm coming from, if I'm coming from the left side or the right side, what number am I going to always be approaching? And the answer is going to be that C value. So in my examples, doesn't matter which X value I'm approaching because my Y value is always going to be what? My Y value is always going to be the constant or the number that they give us. So in the first example, then you're looking at X is approaching 8 over a vertical line, a horizontal line of 11, Y equals 11. That means my answer is 11. The limit as X approaches 0 of -9 is -9. Okay. So of a constant function, whatever that number is, that's going to be your answer. Number 2, limit of the identity. So this is saying, all right, well, if I have X approaching a number and that number is the same thing, what exactly is going to be my answer? So my answer is going to be X, because what this is saying is if I'm looking at 19 and my answer is 19, what does X have to be? Well, you have to look at the constant one beforehand, and the only way that is able to happen is if I have the Y equals X function here, which is that one. And if you think about it, if I was to plot these points, I'm plotting points of 1, 1, 2, 2, 3, 3, 57, 57, and so on and so on. So I'm plotting all those points, so all those points are always going to be the same. And so when I plot all that, I've got this line that's going in that direction there and there. And so since I have that, my Y equals X line, everything is going to be the same. And that's why this piece here is always going to hold true. So if I ever ask you what's the function, and I give you a question mark right here where that X is supposed to be, what's the function of that? The only thing that can fit in there is going to be an X value. Okay. Questions on that one? Okay. All right, let's look at the next one. The sum limit. So this is actually where we're starting to get into some fun stuff. Yes, I think calculus is fun, just to let you know. So don't throw things at me, please. Be nice. So when I have a function, and usually when I have that, it's usually like a polynomial or something like that. When I have those functions and I'm trying to add all of them together, what we're basically going to do is we're going to take those functions and we're going to separate each one of those. And each one of those, we're going to look at the limit of each one. So if I have a function here, okay, so I have some random polynomial here, what I'm going to do is I'm going to take each one of these terms and I'm going to break them up and get two different terms, and then I'm going to evaluate each piece at that limit, and then I'm going to add those together, and that's where my answer is going to come from. So what that looks like is this. I've got the limit of X approaches -3 of X plus 16. So I'm going to take this X plus 16 here, and I'm going to break it up. So here's my X and my plus 16. And then I'm going to evaluate each of those. And then I'm going to add them together and get my final answer. So when I'm looking at the limit as X approaches -3 of X plus 16, I wind up with 13 as an answer. So all it's saying is just take this really big problem and break it down into these smaller little problems and you'll get your answer. So when we talk about a sum, we also have to talk about a difference. It's the same exact property. And the only difference is instead of adding them together, you're going to subtract them. So again, I've got my two functions here. I'm going to subtract them after I separate them. And whatever answer I get, that's what I'm going to come up with. Okay? So again, keep that in mind as you're doing these. Okay? And remember, if I go too fast, the good thing about having videos and stuff, you can just hit pause and write down what you need, then you can keep on going. Okay. Next one. Product. Same exact as the other two. You're going to take them, split them up, and then multiply your answers together. So same thing. The limit of negative 10x, I'm going to take that 10 and that x, I'm going to split them up. And then I wind up with a limit as x approaches 7 of negative 10 times the limit of x approaches 7 of x. Put them together, multiply them out, and I get negative 70. When you talk about product, you also have to talk about quotient, and the same rule is still going to apply. Ooh, did I not talk about quotient? Ooh, guess not. So we'll talk about quotient later. I missed one. All right, the monomial. So this goes back to what I did earlier. Where did I do it at? Oh, maybe I didn't. So the monomial is just your single term. So instead of, let's look at here. Instead of going through this process here, okay, when I'm looking at the monomial, yeah, I can take this monomial here and I can split this up like I did here and get an answer. But if you notice, that takes a really long time to do. With a monomial, basically what we're going to do is we're going to take this answer and we're just going to evaluate it. So I'm going to take my problem, for instance, this one here, as x approaches 2 of negative 7 times x to the third. I'm going to take my 2 and I'm going to plug it in, as I'm doing here, and then I'm going to evaluate it. This is called direct substitution. You just take your number and evaluate. And so that way, you're not having to do all these different properties and steps. You won't have this whole long problem that you actually have to do. So there are shorter ways to do some of this stuff. Okay. From there, we go to the polynomial. Now, again, I can take each one of these if I wanted to, and I could break this up and have the limit as x approaches 2 of 7x to the third plus the limit as x approaches 2 of 3x squared. And then I can take these and break them down again. Or I can just take this and plug it in and get an answer. It's a lot simpler just to take these numbers and plug them in to actually get an answer. And now this is an absolute wonderful idea if you're dealing with a polynomial. And that's going to be the key. If you're dealing with polynomials, absolutely go right ahead, go through the problem, get it done. Don't spend too much time on it. There's other things that you have to do that's going to require your attention elsewhere. And this is one of those that you can just plug and chug and go. Okay? Now, same thing with the limit. I'm sorry, not a limit, a power. So when I'm looking at this, the same thing like what we did back here, where we came in and we plugged it in and got an answer here. Well, if I got this answer here and I want to do the same thing over here, I'm just going to plug in. So I'm going to take this 4 here and I'm going to plug it into that X position there and evaluate. And so that way, again, I'm not having to break everything apart and wind up with all this huge long problems. Because you could, if you wanted to do the long way, you could come over here and say, okay, well, I need to go 3x minus 5 times 3x minus 5 times 3x minus 5. I could do that. And then I can FOIL this piece out here and go through this whole process here and get my trinomial here. And then I have to take that answer and multiply it times the 3x minus 5 and then do it all again and then evaluate. So you see how it just keeps getting longer and longer and longer. You can bypass that by just taking the 4 that's sitting right here and just plugging it into that x value to get your answer. And that's all we did over here. These we took the 4, plugged it into here. So 3 times 4, that's your 12, minus 5, that's where the 7 comes from. 7 to the third power will be 343. Okay? So keep that in mind. Don't make this stuff harder than what it has to be. All right? Then we have roots. Yes, we're going to have square roots. We're going to have cube roots. Usually those are the main twos that we deal with. Sometimes we'll go into the fourth powers. Usually when we get up to those higher powers, fourth power, fifth power, sixth power, they're numbers you actually know how to work with. So if I said, what's the fifth root of 32, you should be able to tell me, well, that would be 2, because 2 times 2 times 2 times 2 times 2 is 32. So there are going to be numbers that you are actually going to have to know, hopefully, and so that way when you're doing these problems, you can evaluate this a lot easier. So you're going to take this, the same thing as you did with the other two. You're going to take your -1 here. You're going to plug it in here, and then you're going to get your answer. So when I do that, I took my -1, I plugged that in, I evaluated it, and I wound up with the square root of 2 as my final answer. Okay? So we talked about the constant, we talked about the identity, we talked about add, subtract, multiplied, we talked about monomials, polynomials, and roots. There's the quotient. So we talked about the quotient too. So when we deal with the quotient, the first thing that you want to be able to do is make sure that your denominator never equals 0. If your denominator equals 0, then you need to do some algebra behind it, or you need to be doing other steps that I'll show you later on. But if you notice in this problem here, if I took my 3x minus 5 and I plugged in my 2, I will not get 0 as an answer. I will get a different number. So I'm just going to be able to straight evaluate this problem by plugging it in. What you do to the top, you have to do to the bottom. So we're going to plug that 2 into the top, plug that 2 into the bottom, evaluate that fraction, and you wind up with a -3. So the key thing, and I cannot stress this enough, is when you do this, you want to make sure that the denominator is not 0. That is the key thing. If your denominator equals 0, you cannot do a direct substitution and you cannot evaluate these right away, okay? You're going to have to do some other things, and I'll show you that a little later on what I'm talking about, but you're going to have to do other things to be able to make sure you're going to be able to actually do this problem, okay? So let's recap. These are your formulas that you primarily have. So you have your constant formula, this one here. You have your identity. And then this is simply saying that for the most part, if it's a polynomial, then you just plug it in and whatever that answer is, that's your y value, and you get that as an answer. You have your sum, your difference, and your product. Okay, so notice you just evaluate these as is. Then you have your power rule, and then you have your root rule. And then you have the quotient rule. The quotient rule says basically take the limit of the top and the limit of the bottom and make sure your bottom does not equal 0. So those are your properties that you're going to need to know and make sure that you understand how to use them. So let's get a little practice in, okay? Here are 6 problems. Plug these in, see what you wind up getting. Yes, there is trigonometry on here. Now, before you get into this, let's talk about a little bit of this trig stuff. You are expected to know your unit circle. Your unit circle, you need to know it like the back of your hand. If you do not know that unit circle like the back of your hand, pull out the stuff that we did last year and start memorizing it again, because this is something you need to know. Here is your hint. If you are ever on the non-calculator portion of the AP exam, my test, whatever it is, if it's a non-calculator portion and I give you a trig function and I'm asking you to evaluate said trig function, it will be on that unit circle. No ifs, ands, or buts, it will be on the unit circle. So if you're looking at something and you're going, I have no idea what, tangent of the square root of 57 is. Well, you've done something wrong, or you're on a calculator problem. One of those two things have happened. So if it ever asks you to do this by hand or by, no calculator or by memory or something, it is going to be on the unit circle. So keep that in mind. That is going to be huge, and you need to make sure you know it, okay? So I'm going to give you a few moments. Take your time, hit the pause button, and once you're done, hit play to check your answers, okay? Talk to you in a second. All right, welcome back. Let's look at your answers. Here is A, B, C, and D. So A is 16, and then 20. That's simply 0, and then 3. And then here is E, and there is F. Now notice this right here. I did not write the number 49. Why is that? Well, here's the deal. In calculus, if you get to this portion here, and it's nothing but numbers, and either your calculator dies, or you're not confident that you can enter it correctly, or you're not confident of your PEMDAS skills or whatever else, you are absolutely okay, 100% able to stop right here on a free response question. On a free response question, you would get full points for 3 plus 4, all of that squared. It doesn't matter if you have 49. You don't have to have that. If you can get to 3 plus 4 to the second power, you are good to go. You don't have to do anything else at all whatsoever. Now, again, that's only on free response questions. If you're on a multiple choice question, then you're not going to have 3 plus 4 squared. You're going to have 49 as an actual answer. Okay, so those just something that you need to keep in the back of your head, because if you notice on which one, C, the same thing on C right here, I can leave it like that. I don't have to put in 0. Because the fear is that you do something and you lose points because you've made a sign error or something. If you get to a numerical value, you can stop. You don't have to do anything else. So 0 over pi is the same thing as 0, so you don't have to do anything else. They're equivalent. The same thing with this right here. Now, this one up here, you can't stop there, because what is the cosine of pi? You actually got to tell me that one, so you can't stop there. On D, I could have stopped right here if I wanted to. I didn't need to give you 3. I didn't need to give you this one here either, okay? On free response questions only, multiple choice questions are going to have these as your answers, okay? They're not going to have that as an actual answer. All right. So we talked about limits. We talked about what it is. We talked about finding it from a table. We talked about finding it from the graph. We talked about looking at all the different properties. And we talked about direct substitution. So let's actually look at limits, because if you think about it, I told you in the beginning, a limit is when you're approaching the same thing from both sides. But the question is can you have what's called a one-sided limit? The answer is yes, you have to. Okay? When you approach a limit, you're always going to approach it from two sides. That forces this piece here to happen because I'm approaching this intersection here. Well, if I'm approaching this intersection here, am I approaching it from this side? Well, the answer is yes. Am I approaching it from this side? And the answer is yes. But if I take this piece out, because I'm only driving one way, if I'm driving down the street, if I'm going northbound on a highway, do I care what the southbound's going to do? No. I only care what northbound is, and I'll care about, am I going to approach this stop or this crosswalk there? The answer is yes, I'm going to approach it. I'm going to approach it from the left side. I'm going to approach it from the right side. But as I'm the only driver of my car, I'm only going to approach it from one of the two sides, not both at the same time. And that's what a one-side limit does. It only focuses on what you're approaching either on the left side or the right side. Okay. So left-hand limit. You will notice, it's going to be a left-handed limit if you see that little bad boy right there. That little negative to the right of the number in question. Okay. That negative sign tells me, or tells you, not me, well, I guess it's me too, but tells you that you were approaching something from the left-hand side. So as I'm approaching from the left-hand side, I don't care what's happening to the right-hand side. I don't care what I'm approaching from the right-hand side. I only care about the left-hand side. Okay. If I'm looking for the right side, the same thing, but I only care about approaching it from the right side. Now, that plus and minus, that doesn't necessarily mean that my answer is going to be a positive answer or that my x value is going to be a positive value. No, it just tells you direction. It has nothing to do with the sign that sits in front of the number that you're looking at because it doesn't sit in front of anything. It's up in the air like a superscript, and it's telling you, hey, we're looking at this number, but I only want to look at it from the left side, or I only want to look at it from the right side. Okay? So when you're looking at a one-sided limit, pay attention to the pluses and minuses. It's going to be huge going forward. When we have one-sided limits, that does mean that sometimes we're going to have limits that do not exist. Okay, let me say this again. Because we have one-sided limits, that means sometimes we're going to have limits that do not exist. That means I'm going to approach something from the left-hand side, and it may not necessarily be the same number that's coming from the right-hand side. Okay? I might be on the same x-axis that I'm looking at, or the y-axis that I'm looking at, but I may not necessarily be approaching the same thing. The only way you can have a limit is that you must approach the same thing from both the left and the right side. If you are not approaching the same thing from the left-hand side and the right-hand side, you are not going to have a limit. They have to approach the same thing from both sides. So that's the difference. If your values of L and M, if they do not match, if they do not equal each other, your limit does not exist. That does not mean that your limit from the left doesn't exist, because sometimes it may not, but the majority of the time it will. That is saying that the whole overall limit, that doesn't exist. So I can be approaching a number from the left, I could be approaching a number from the right, and if there are two different numbers, then the overall limit doesn't work, but the individual limits will work. So let's look at this. So I'm going to look at this piecewise function, and usually this is where the majority of your limits come into play that don't exist or that do exist. That happens with piecewise, okay? So what I want to do is I want to look at this and I want to say, okay, well, I've got this limit here. And I want to figure out, I'm going to focus on 0. So that's going to be my whole entire thing. So the first question they're going to ask me is, well, okay, am I defined at 0? And if I'm defined at 0, what exactly am I going to be defined at? So let's take a look at this here. Give me just a second. Miss Mason's asking me a question, so hold on. Okay, that's good. So what's going to happen is that I'm going to look at 0 here. And I'm going to come in and I'm going to say, okay, well, what is actually f of 0? Well, f of 0, I'm either going to have this answer or this answer. Well, I have a closed dot, so I'm actually defined on that dot, and that's going to be 1. Okay? Now, coming from the left-hand side, I want to now focus on that. So that negative sign says coming in from the left-hand side, what number am I approaching? Well, coming up from the left-hand side, I'm going to approach the number 2. So then we're going to look at the right-hand side. So I'm going to clean this up a little bit so you can see what's going on. So coming in from the right-hand side, I'm approaching a number. I'm approaching the number 1. So the question is am I approaching the same number from both sides? The answer is no, I'm not. So because these two here are not the same, my answer does not exist. Okay? So in order for this to have an answer here, you have to have the same numbers here and here. Let's try it again. So I'll give you a couple moments. See if you can try to figure this one out. Okay? Hit the pause in the video, work this problem out, and when you have it worked out, hit play. All right. Welcome back. So if you notice that this is the number I'm going to be looking at. So when I'm looking at this, this is what I'm asking myself. I've got the limit of f of x as x approaches 1. I want to know, does that exist? How I got this is if you take a look at what you're focusing on, notice the ones there, that's going to be the value that I'm going to focus on. So because of that, then I'm going to come over here and say, okay, I'm going to look at it from the left-hand side. I'm going to look at it from the right-hand side. Notice that my two answers are different, so therefore my limit does not exist. All right. So I'm hoping that so far I haven't lost anybody. I hope I'm getting good questions, going forward with this. So it's just practice, lots and lots of practice, okay? So a note. So this kind of brings everything together. So when we're talking about when limits do not exist. So go to a highlighter. F of x approaches a different number from the right side of C than it does from the left side of C. So when you're looking at that, you have to approach the same value in order for something to exist. If it increases or decreases without bound, what does that mean? Basically, what that means is that you have an asymptote. So if as I'm approaching C and I wind up coming up to, let me try that again. Is that and that? Let's say I'm going to approach, not that, let's try that again. Okay, I'm going to approach this number right here, but I know that here I've got an asymptote right there. So that means as I'm approaching it from this area without bounds means I'm going to go off into infinity. or I'm going to go down to infinity. That's what it means for increases or decreases without bound. All right. So that's what this second one here, what this is talking about. It's talking about increasing or decreasing without bound. So I'm going off to positive infinity or negative infinity. The last one oscillates. So what this is saying is that I'm going to bounce up and down between two specific numbers. Let's see if I can actually do this. So something like that. Well, actually, maybe not. Maybe it's going to be a little bit more. Something like that. Okay. So I'm going back and forth. 99.9% of times, these are going to be something involving trigonometry. So if you oscillate without bound, then you're not going to have a limit. Okay. All right. So those are the three ways that things don't exist. Final question here. What happens when my denominator equals 0, but the graph shows that it exists? So when I mean when the graph shows it exists, that means if you're looking at your calculator, you have a hole. So what happens when you have a hole? What do you do? What happens when your denominator goes to 0? What do you do? Well, one of the things that you can possibly do is see if you can factor it out. There is another way that we'll learn later on in the school year, but for right now, you don't have to worry about that one. So your go-to one for right now is going to be, can I factor this? So we're going to look at that. I give you this problem. And if you notice, when I plug in that 1, my 0 goes, or my denominator goes to a 0. So what do you have to do? You have to do algebra. That's all it is. So we're going to say, okay, well, what can I do? I'm going to take this numerator up here because it is a quadratic and it's something that you can do. I'm going to take that numerator and I'm going to factor that down to see if I can cancel something. And sure enough, I can do that. So when I take that, I take my 3, factors of 3 that subtract to give me a 2. That's x plus 3, x minus 1. Well, both of my x's minus 1, both of my x minus 1s cancel out, leaving me with x plus 3. So now, instead of taking the limit of this whole thing here, I'm no longer going to do that. I'm going to come over here and say, okay, well, instead of doing that, I'm going to take a limit of this bad boy right there. I'm going to come over here, take that limit, and I will get a 4 as an answer. Okay. I know I just gave you a lot of information. I know this is all new and everything else. So, go back, look at parts of the videos that didn't make sense. Please make sure you are emailing me. Please make sure you are sending me remind questions if you need to or whatever. But either way, just keep talking to me so that way I can go through and make sure that you are understanding everything that you are doing, okay? Make sure if you're asking me questions, please make sure that you are sending me a picture of what it is that you're talking about as well. If there's no other questions or I don't have anything else for you, so let's go off and it's going to do some work and I will talk to you soon. TTFN. Ta-ta for now.